Welcome to This Explainer. Today, we're going to unpack something really cool. The invisible mathematical language that literally governs everything in our world. And I mean everything. From the simple, mundane routines you do every single morning, all the way up to high-stakes space exploration. We're talking about mathematical functions. It's the ultimate language of relationships. And by the time we wrap up here, you're going to see exactly how these mathematical rules are just quietly running the universe right in the background.
Okay, let's dive into this. How in the world is an everyday, ordinary vending machine sitting in an office break room identical to a billion-dollar satellite orbiting the Earth? I know, it sounds totally absurd, right? But mathematically speaking, they actually operate on the exact same underlying logic. To see why, let's use that vending machine as our foundational model to really ground this idea. When you walk up to one, you have a very specific expectation. If you press button A, which is your input, you fully expect to get a specific product out, like a can of Coke. That's your output. Pressing a specific button always yields one specific product. There is zero randomness here. The machine connects your input to a highly predictable output. And you know what? A mathematical function works the exact same way.
So the crucial point is that a function acts just like this universal machine. It's basically a three-step process. You start with step 1, your input. You feed that into step 2, the function itself, which acts as the machine's internal mechanism or its rule. And then boom, that gives you step 3, the output. For every single input you drop into this machine, there is only one possible output that can pop out.
That brings us perfectly to our formal definition. A function is a mathematical rule that connects an input to exactly one output. I really want to hammer that phrase home for a second. Exactly one output. Because think about it, if that vending machine sometimes gives you a Coke, but then sometimes gives you a completely different soda when you press the exact same button, well, the machine is broken. In math, this golden rule, exactly one output per input, is what makes functions incredibly reliable, powerful tools for modeling reality.
Let's put some numbers to this and map inputs, which we'll call x, to outputs, which we'll call y. With a super simple rule, say y equals 2x, the consistency is just perfect. As your input scales up, the output predictably doubles. Every single value that gets processed by this rule conforms to that strict, exact relationship.
The exact same logic applies to a rule like y equals x squared. Now here, the outputs are scaling exponentially, sure, but it perfectly maintains our golden rule. Every x yields one and only one specific y. The internal mechanism of the machine is a bit different, but the absolute reliability of it remains exactly the same.
Now, you might be wondering, why do engineers and scientists actually care so deeply about this? Well, it's because functions describe real relationships between quantities in the real world. Engineers rely on these exact relationships to predict how one variable is going to change the split second another one changes. They use functions to figure out how speed changes over time, or how fuel consumption changes depending on the mass of a spacecraft. They use them to model how temperature fluctuates during a satellite's orbit, or how a battery's voltage drops while it's discharging. Functions are quite literally everywhere when we need to predict reality.
And this brilliantly illustrates why functions are used for some of the most complex, high-stakes tasks humanity has ever tackled. Think back to that billion-dollar satellite I mentioned earlier. Imagine a satellite traveling in orbit at a constant speed of 7.8 kilometers per second. That is an absolutely staggering velocity.
As that satellite zips around, the underlying rule is beautifully simple. Distance equals speed multiplied by time. So whether we're looking at 10, 20, or 30 seconds, simply by knowing the time, which is our input, we can calculate the exact, precise distance it traveled. The satellite's position is, fundamentally, just a function of time. Let's look at another epic space example. Spacecraft run on electricity, right? And they generate that from solar panels. But that power isn't just some constant static number. It depends heavily on the angle of those panels relative to the sun. As the angle changes, the power generated changes right along with it. Therefore, power is a function of the sun angle. By treating this whole thing as a mathematical function, engineers can accurately predict exactly how much electricity a spacecraft is going to generate at any given moment throughout its entire orbit.
To really grasp these relationships, engineers don't just stare at raw data sheets, they graph them. When we plot these functions out visually, like our y equals 2x rule forming a perfectly straight line, it lets engineers instantly see the shape of the relationship in a single glance. It immediately reveals the rate and the nature of how the output dramatically changes as your input changes. Now, instead of always writing y equals x squared, mathematicians use this highly efficient shorthand, f of x equals x squared. I know algebra notation can look a little intimidating at first, but let's completely demystify this. All you have to do is read it out loud, literally like a normal sentence. It just means the function f takes an input x and returns x squared. That's the whole shebang. F is simply the name we're giving the machine.
Let's move to and see how this builds into real practical application. Actually, evaluating the function is incredibly simple. If our function returns the square of the input, well then f of 2 equals 4, f of 5 equals 25, f of 10 equals 100. It's just a really elegant, clean way of showing exactly what went into the machine and exactly what came out.
So let's take a quick step back and summarize the actual mechanics of a valid function. Every single time you build or analyze a function, you need three absolute must-have components. First, the input, also known as the independent variable, which is the value you choose to put in, usually x. Second, the rule, which is the actual mathematical operation happening inside the machine. And third, the output, the dependent variable or the final result, which is usually y.
Now, what's really interesting about this concept is how it clarifies a super common trap people fall into regarding our golden rule. Remember, the rule is that each input has exactly one output. But here's the catch. Different inputs can actually share the exact same output. For example, in our squaring machine, f of 2 equals 4, but f of negative 2 also equals 4. And you know what? That is totally fine. The machine isn't broken. What is strictly forbidden, no exceptions, is one single input spitting out two completely different results.
Grasping this simple but incredibly strict rule is exactly why functions are the absolute foundation of almost every single engineering and scientific subject on the planet. I mean, from physics, whether we're talking motion, force, or energy, to control systems and signal processing, machine learning, orbital mechanics, spacecraft thermal analysis, communications, they all rely heavily on this stuff. The scale of this topic is just massive. Understanding functions is an absolutely crucial skill because anytime one quantity depends on another, you are working with a function.
Which brings us to the end of our explainer today. We've journeyed from a simple breakroom vending machine all the way to a satellite moving at 7.8 kilometers per second, and they are perfectly connected by the exact same mathematical logic. So, I want to leave you with a final thought to ponder as you go about the rest of your day. Just look around you. Whenever one thing changes simply because you changed something else, a mathematical rule is quietly at work. So, what hidden functions are operating in your life right now?